Okay. Well, it's a bit late, but let's start now. So this is a historical example known to the Greeks and also to the times of Islam, I guess. It is a float that is used in the toilet flushes nowadays. You see the level of the water is kept constant by the float over here. By the way, can you see the cursor? Can you?
Yes, sir.
The float stays on the top of the water, and as you see, as the level of the water rises, the float goes up and it closes by this mechanism of the lever, it closes the valve coming inside, and therefore the water coming in from the pipe is stopped so that it doesn't flow anymore. So the level of the water remains constant. Whereas if the level drops somehow, this float goes down, which opens the valves and lets the water in. So the basic idea is this system, by the help of the device called float, is self-regulating. It regulates its own height or level. Okay, without our intervention, this device keeps its height approximately constant. Okay, so it is a self-regulating machine, a very simple one, but still, the idea is quite clear. There is a control device, there is a sensing device, there is a control device, and there is an actuating device, which keeps the level constant. It is a simple example that is even used nowadays. Now, one of the first applications of the control systems is actually the regulator or the flyball regulator, flyball governor in the steam engine, which was devised in around 1775 by James Watt. This basically generates power from the steam. And as you see, this is the working principle, as you see. The steam comes inside. There is a valve here which opens and closes, and well, the pink color shows the hot steam, and the blue color shows the condensed steam, so that the energy of the steam moves the piston back and forth and makes this device work. Well, this was the motor of the Industrial Revolution, or maybe we should say the first Industrial Revolution, which increased the capacity of production enormously in the 19th century. Now, the problem with the steam engine was that the speed of the steam engine varied too much. That is, the speed of this shaft that is rotating was varying, well, to a great extent, and that made it unusable because we needed more or less constant speed from an engine. So James Watt devised this steam engine governor, which basically is something that keeps the speed of the engine constant. And there is an animation here which shows how it works. Basically, the governor is two metal spheres that rotate, and that rotation is connected to the output shaft of the engine. And the motion of those spheres is somehow connected to the steam valve. And if the speed of the governors increase, if the governors open up, the mechanism somehow closes the valve or lets the valve flow from the valve decrease, because it introduces an obstruction to the steam pipe. Therefore, the steam coming to the engine, the volume or the, let's say, flow rate of the steam coming to the engine decreases as the speed increases, okay? And vice versa. If the speed decreases, it opens the valve and the steam coming to the engine increases. So it tries to keep the engine speed constant, as you see, by an ingenious mechanism called the steam engine governor. James Watt actually, devised this and took the patent of it. And at those times, people didn't have didn't have the mathematics and knowledge we have today, but they could devise such mechanisms. The problem is this device, where sometimes it worked, sometimes it didn't work, okay? Sometimes it worked perfectly, and sometimes it went crazy, it went unstable. And people didn't know why, and they tried to correct it. Until, I think, 1870s, in James Clerk Maxwell wrote a paper on governors, and he basically explained the stability of these devices, but we will come to that later on. There is not much, we don't have to go too much in detail, but this is one of the first applications of control systems. As you see, the steam engine governor regulates the speed of the engine. Another application, one of the earlier applications, is the autopilots used in the airplanes. And this is a autopilot that is used in a mechanical autopilot used in an airplane. The airplane has three control surfaces: aileron, elevator, and rudder. All of them are controlled by, as you see, by gyroscopes and some hydraulics, which makes the task of the pilot much easier. An airplane with an autopilot is much easier to fly. Okay, without an autopilot, the airplane is very difficult to control and tiring to pilot, let's say. And this is one of the designs that was used in 1930s. Well, obviously, later on, the Apollo program that landed a human being on the moon was made possible by the advanced application of control systems. To send a rocket to the space and then to send it to the moon and make it land to the moon, and then go up from the moon and come back to the Earth required a lot of control systems. And the technology the computing technology they had at that time was much less than what we had. Probably their computers were less powerful than your cell phone those days, but they could, land on the moon and come back, which is a enormous accomplishment, and that was made possible again by, partially at least, by the developments in the control systems. One control system that is commonly used in our everyday life is a temperature control system, which most of us use. As you know, if you are in the winter, you use a heater. If the temperature of the room gets hot, you turn off the heater, and if it gets cold, you turn on the heater. You can do it manually by hand. Many of us do it that way, but then it's possible to do it automatically. You just put a temperature sensor and measure the temperature, and compare it with the required temperature. As you see, this is a, let me see if I can do it. This is a plus and this is a minus. So this is the heater is driven by the difference between the measured temperature and the required temperature. If it's negative, which means that if it's negative, it means that well, if it's positive, okay, if it's positive, the temperature is less, the temperature is less than the input temperature, in which case the heater keeps on heating the room, and when it becomes negative, the heater stops, kind of. It can be an on and off controller, for example. This is a simple on and off controller. But the main thing is, here we have a feedback loop. This is the forward path, and this is the feedback path. And the feedback path, we have a sensor. The sensor measures the temperature and controls it with the, compares it with the input to the system. So this is a very, very basic control system again, which is commonly used in daily applications. And in the feedback devices are usually represented in the following block diagram form. There is the output response and there is the desired response. We want the output response, which is this one, output response, and this is the desired output response. We want these to be equal to each other, more or less, okay? So the output should be equal to the desired output. That is our aim. And there might be, I didn't show it here, but there might be disturbances to this system also. So the process you want to control has an output and it has an input also. Input, let's say here. Input is generated by the controller plus the actuator here, let's say. Plus the actuator, this is a plus. The process is, output is measured by the measurement device and it's compared with the desired output. The difference drives the controller and the actuator, and it just changes the response of the system. And it tries to keep the output response to the desired output response. It tries to keep it equal. That is the idea here. By use of the so-called feedback. This is the forward direction from left to right. And from right to left, you have the measurement device in which you have the feedback. You are feeding it backwards. Okay, that's why we call it a feedback system. For example, while you are driving a car yourself, this is a manual control system. That is, a human controller is in charge, but it can easily be nowadays we have actually automatic control systems for directions of the cars. The car has a course of travel, and there is a desired course of travel, which is dictated by the road, let's say. When the human drives a car, basically he or she sees how the road turns. Therefore, by visual measurement, we see that how the road turns, and we try to turn the steering mechanism. The controller is the driver here, uses the steering mechanism in order to drive the automobile, the car, in the actual course of travel. So if the desired course of travel is this black line, and if the actual direction of travel is this let's say the blue line, it more or less corresponds to each other. Now, instead of the manual driver, you can put a camera here which senses the road and its direction, and you can, make the road follow the direction of the car. You can also use, for example, the speed control for a car using the gas sent to the engine by the let's say carburetor, or by the well, whatever device, the valve that comes to the internal combustion engine. So the speed control is another possibility. Now, an interesting device is the inverted pendulum. I will show you in a video soon. You have a pendulum that stays upwards like this. A pendulum, that is upwards cannot stay upwards by itself. It is inherently unstable. A pendulum, if you put it upwards, if you put a stick upwards, it will eventually fall down because it is unstable. Okay? So this pole, the stick, by itself is unstable. But if you put it on a cart and if you apply a force on it by measuring this angle theta, if you apply a force on this cart and push this cart back and forth, this pendulum is going to, you can stabilize this pendulum and keep this pendulum upwards. And it's not only that, you can just, of course you have to measure this angle theta and maybe theta dot. You can do it for double pendulum or triple pendulum as well. You can stabilize such devices, and it is an interesting application of control systems. You can stabilize systems using control systems. And there is a video here. I wanted to show it to you.
All right, so here we have an alternative inverted pendulum setup, in this case a linear one.
It is, actually it starts from bottom.
Moves this cat.
It will, put it upwards and keep it upwards.
Not actuated at all. So the idea is that by moving this cat, I should be able to balance the pendulum in the upright position. So now let's see a demo of this pendulum in action.
This is just by itself.
So now we have the controller running and the cat stabilized in the upright position. It's using two sources of feedback. One is it's getting the angular position of the pendulum rods, and two is it's getting effectively the cat position from the angular position on this drive motor. As you see, we can reject disturbances. I can try and push the cat around. We'll find that off. And you can even reject disturbances on the pendulum motor, obviously it's much more sensitive to that. That's a tough disturbance to reject. Now, in a sort of swing up demo that you saw earlier, there were actually two controllers in operation. You use the rule-based controller to execute that swing up maneuver, and then once it got into the capture range, you switch to this more conventional portable control.
Okay, as you see, you can stabilize not just one pendulum, but two parallel pendulums, but you can even stabilize double pendulums on top of each other, and you can find it in the YouTube, lots of YouTube videos about these. I'm not going to show it here, but I just wanted to show this one.
Hojam, I had just a question about the inverter.
Yes.
Could you explain again what's the purpose of that system? How can we use that in
the inverted pendulum, you mean?
Yes. Yeah.
Well, it is actually, it is a nice demo system which shows you the capabilities of control systems, but it can be a model of a vertically, flying, vertically going up rocket. The rockets themselves are inherently unstable when they are going upward, when they are going vertically. So you have to stabilize them by thrust vectoring or something like that. It can be a model of a rocket that is going upwards vertically, for example. And there are other applications of, well, it basically is this one we have is a toy which shows the stabilization, possible stabilization by control systems. And controlling double or triple pendulums is a kind of a difficult control problem, which is usually commonly done in engineering classes. But otherwise, there are not too many applications. The pendulum that is downwards, not inverted, but the downward pendulum has an application that is a crane moving in a production line. If you move a crane with a load on the bottom too fast, it will oscillate too much. So you might want to move a crane with a certain speed without too much oscillations, for example. That is one possible application. Okay, so the block diagram again is the following. Actual output and the desired input is here. Again, one thing that is missing is the disturbance coming to the system. But this is a more, this is the input coming to the system. The actuator generates the input. The control device drives the actuator. The error drives the control device, and the error is generated by comparing the output and the measured output. But how do you compare these two, by the way? For example, how do you make the subtraction? You usually do it electronically. That is, doing these operations electronically is not too hard. Also, you can do it by microcontrollers or microprocessors. So such is the block diagram of a control system. And the main devices are control device, actuator, and sensor. And obviously, there is the process you want to control. You can control a system, for example. Yes, somebody asks a question. Go ahead, please.
Hocam, may you explain again what are minus and plus representing?
Well, okay. Just a second. How do I go back? Basically, here, what you do is the error. Sorry. Error, which is this thing, is equal to desired output minus the measured output. So we have to subtract the measured output from the desired output so that, for example, think about it. If you, as I gave you the example of temperature control, if the temperature in the room is, let's say, 20 degrees, but you want 25 degrees, okay, the error is going to be 25 minus 20, 5 degrees of error, and that 5 degrees of error drives your control device, and that drives your heater so that the room keeps on heating up. And eventually, as the measured output becomes the same with the desired output, the error becomes zero. And when the error is zero, the heater stops. It doesn't heat anymore. And what happens? Because of the loss of heat, eventually the temperature is going to drop. And then the error is again going to be positive, and then it will start again. The heater is going to start again. So error is the driving, let's say, variable that drives the control device. Is it clear now?
Yes, hocam. Okay. Thank you so much.
Okay, as I said, we can do manual control for simple systems. For example, if you have a single tank, you can put a human operator, and the human operator can observe the height, and it can, regulate the valve manually. This is possible if you have a single tank, although, hiring a human is probably too much just to do this task, but it is, humanly possible. But if you have something like this, a boiler control system, boiler generator, you have 3 valves which have to be controlled in the same time, and you have many measurements coming from your turbine, generator, and shaft. You have pressure, temperature, and oxygen measurements, and that regulates the valves, 3 valves from feed water, fuel, and air valves. In the same time, a human operator cannot do that. Even 3 human operators cannot do that. Okay, you have to have a coordinated system with a computer to do this. And this is, for example, a typical application of a modern control system. It is not very easy to design such a system, but it is possible. Okay. So the whole boiler generator system, power plant, is controlled by a control computer and also the sensors and the valves. As you see, it is a quite sophisticated control system, which is humanly not possible to do. And the same applies for things like Apollo control system and so on. As I have said, the task of the controller we have over here, which was a control device, is usually replaced by the computer. What we call a computer is nowadays is a microcontroller or a microprocessor. So the error signal is sent to the computer, and the signal that drives the actuator comes from the computer, and the rest of it, this part of it is digital, but the rest is the analog world. So nowadays we use computer control systems much more commonly than the others. Some examples is, for example, a robotic arm, dexterous hand, which holds a ball inside this hand. This is has 18 degrees of freedom, for example. And all these devices you see, what was it called, the Boston Dynamics examples, are made again possible by use of control systems, obviously. This is a kind of an old picture, a robotic hand for sample preparation. This is from 1993. It is kind of ancient, as you see. There are much more sophisticated examples, but this one operates in high speeds. Another interesting thing is for example, the blood glucose level control for diabetic people. For people with diabetes, the blood glucose level cannot be controlled by the secretion of the enzyme insulin, as you see, from the pancreas, because the pancreas does not work properly. So the people are diabetic. For such people, there are devices which try to control the blood glucose level by measuring the blood glucose level and secreting, pumping insulin to the body. But these devices have to be very precise, because if you pump too much insulin, the person can get into hypoglycemia and die. It's even possible to die in such cases. So this is the blood level blood glucose level and the insulin level of a healthy person. But for a diabetic person, this cycle does not work. So what we do is we have a human body. There is a motor pump and valve. There is a insulin sensor, and there is the desired glucose level is measured and compared with the measured glucose level, and then there is an amplifier which drives the motor pump and valve, which sends insulin to the body. As I said, this is a difficult control problem because it has to be very precise, but it is doable and it is done. Actually, it is being done. Now, these are the examples I wanted to give you. Now, I just want to talk about a little bit about the outline of the course. Basically, we will be talking about 3 different topics. We will start with the modeling of systems, engineering systems such as mechanical, electrical, electromechanical, fluid and thermal systems, how we model them by differential equations, and then how we take the Laplace transforms of them. This will take about 1 month. The second month is going to be system properties and response. This has to be transfer functions, not transfer. There is a T here. Transfer functions, well, this was a bit fast. This should be not response, but response. We will be using Laplace transforms, transfer functions, poles, zeros, and transient response of different kinds of systems. And then this will take again another month. And finally, we will look at the basics of control systems such as stability, steady state error, PID control, and frequency response of systems. This will take another month. So in 3 months, we are going to be covering some basics of basic components of control systems. As I said, this will be a basic introduction, but it will make you understand what goes on and prepares you to further studies. Okay, so much for this presentation. Do you have any questions? Are there any questions? Most of you have turned off the cameras, as I see. So this, as I have said, is a introductory, non-technical lecture, in which I try to, arouse some interest with you. But from now on, it will be more mathematical. I hope you will like it as well, but it is going to be more on the theoretical side. Are there any questions?
Hujam, I have a question.
Yes.
So you said the course has a bit of mathematical side to it and theoretical. So is it like less math or like more theoretical? How does this course go?
Well, I try to use mathematical and theoretical kind of synonymously. Okay, it's more mathematical than your usual courses. Okay, but not too much. We will be using differential equations and Laplace transforms basically, and some, solving differential equations and so on. Calculus. Not too much mathematics, but there is some, not extremely advanced mathematics, but, moderately advanced mathematics will be used.
All right, thank you, Hujam. Okay,
you're welcome. Okay, if you don't have any questions,